Um, okay, so these last few weeks, we've been talking about representation of data structures, and we're still on the topic of representing data. And the particular problem that we're looking at today is data types, different kinds of data, and the interaction between data types and the operations that we want to perform on them. And there are three big ideas for the week. They are type tagging, data-directed programming, and message passing. So to start with, the first problem we're going to solve is this one. At the beginning of this chapter, you saw an abstract data type for rational numbers that was a pair with the numerator in the car and the denominator in the coulter. And you also saw an abstract data type for complex numbers that had the real part in the car and the imaginary part in the coulter of a pair. And that all works great if you're only dealing with rational numbers or you're only dealing with complex numbers. But let's say you want to write a program that works for any old numbers, and you come upon a pair whose car is 3 and whose coulter is 4. What is it? Well, you don't know. So the solution to that is type tagging, and it's going to seem like a ridiculously trivial idea to spend time on until we start talking about it a little more. The idea is this. We represent 3/4 as a pair whose car is the word rational and whose coulter is what it used to be. And we represent the number 3 plus 4i as this structure. Okay? So these things, rational and complex, are type tags, and we have an abstraction for tagged data that you can see up in the top half of the screen. So the constructor for tagged data is attached tag, otherwise known as cons, and the type tag is the car, and the contents is the coulter. Okay? As I said, a pretty trivial idea. But there are some more things to say about it that might make it more interesting. And the first thing to say is that inside a scheme interpreter, it has to do something very like this for its data types. Because as you're going to learn in detail in 61C, and as they told you, probably starting in 3rd grade, inside the computer, there's nothing but ones and zeros. And you take a pattern of ones and zeros, and you give it a meaning by some convention. So the same pattern of ones and zeros can be an instruction to the computer, like move this from here to there. Or it can be an integer. And there's slightly different representations for signed and unsigned integers. And why is that? Because in a computer word, which is 32 bits, 32 of those ones and zeros, mostly, although you're starting to see 64-bit ones. But let's talk about 32 bits because the numbers are easier to grasp. You can represent about 4 billion values. So your choice for integers is whether you want to represent 0 to 4 billion, roughly, or whether you want to represent -2 billion to +2 billion, roughly. So by getting negative numbers, you lose sort of half of the magnitude. So there are these two different formats, and then there's a third format for representing numbers that aren't integers, that have a fractional part called floating point, which is extraordinarily complicated in its details, and you'll learn a little bit about that in 61C also. So since all of those things are just patterns of ones and zeros, and since every possible pattern is meaningful as an integer, and pretty much every possible pattern is meaningful as a machine instruction or as a floating point number, Scheme can't tell just by looking at that pattern which thing it's trying to represent. Oh, and another thing it can be is a pointer. So a pointer is something that says where in the computer's memory something is. So a pair, for example, is made up of 2 pointers. So that's yet another data type that the same patterns of 1s and 0s can represent. So what Scheme does is something very much like this, where it attaches a type tag to every value. And typically, in an interpreter, the type tag is not a word like rational or complex, a text word. It's a pattern of just a few bits, because there are only, half a dozen or so types that you need to represent. So they take 3 or 4 bits carved out of some place and use that as the type tag for each value. So every interpreter for a Lisp-like language, including Scheme, does type tagging of the data this way that we're talking about internally. Some other languages don't do that, and this is why it's worth talking about and not a trivial idea, because there are implications either way. So in that language you learned in high school, you say things like integer, I comma j, and maybe you say float or something, x comma y, right? And you will have noticed this semester that there isn't anything like that in Scheme. You don't have to say when you create a variable by define or let or whatever, what kind of value goes in it. Okay, whereas you do in these other languages. Typically, languages that are mostly compiled rather than interpreted make choices like this, meaning that you write your program and you run it through a compiler, and out comes a machine language program which you then run, as opposed to something like Scheme where you type in an expression and out comes a value, and you type in another expression and you can interact with it. So why do they do this in these languages? What it buys them is this. Computers have these different representations, the conventions about how to interpret the bits built into their hardware. So in whatever computer you're using, there's going to be an instruction, typically with a name like add, and another instruction with a name something like floating add. Okay? And because of these declarations, if you say I plus j, the compiler for Java or C++ or whatever it is you learned knows that it should do integer add. Whereas if you say x plus y, the compiler knows that it should do floating add. Right? And therefore, at compile time, we already know what kind of arithmetic to do, and we can compile this into exactly the right machine instruction. Scheme doesn't know that. When you say something like I plus j in a Scheme program, we don't know until the program is running what kind of thing the value of those variables is going to be, right? Because in Scheme, you can make a list of numbers, and some of them are integers and some of them aren't, and it all just works. Okay? So the disadvantage that we get from using type tagging, in other words, from associating types with values rather than associating types with variable names, the disadvantage is that our programs run a little slower, because the Scheme interpreter sees, well, it doesn't see I plus j, it sees plus ij. And it has to say, well, let me look at I and see what its type tag is. Let me look at j and see what its type tag is, and then do whichever of these is right. By the way, what if you say I plus x? What happens? Well, something more complicated, because you can't, the machine doesn't know how to add an integer to a float. So what happens is you call a procedure that says typically convert the integer to a float, and now I have float plus float, and then I can do the computation. And the compiler has to think about that case also, as does the interpreter, right? But the compiler does it before you're even running the program. So if you're in a situation in which you're going to write a program, and once it's written, it's going to be used every day until forever by some company, then it's a good idea to put as much of the work as possible on the shoulders of the compiler. Because when the program is running every day, it then doesn't have to do this kind of analysis. It's just ready to roll. On the other hand, at kind of the other extreme, if you're, let's say, a student in a computer science class, basically your programs never go into production. You're only interested in a program as long as it's not working, right? And once you get it debugged, you go on to the next exercise. So for you, what's important is not the running speed of your program so much as the running speed of the whole process of reading what you type and figuring out what it means and doing it. So we don't really suffer from this time efficiency problem of using typed data instead of typed variables. And we get an advantage. The advantage we get is this. It's really easy to do heterogeneous data. Okay? So I can come over here, and I can make a list that contains an integer and a non-integer. It's not going to remember all those digits probably. And a word and a list. And that just all works. Okay? If this were a list of numbers, I could write a little program to add them all up, and my program wouldn't have to worry about is this thing an integer or is it not an integer? Right? So what you have to do in this kind of language is stuff like okay? Since variables have to have their types set ahead of time, if I want to write a procedure to square a number, I have to write one for integers and a different one for floats, and I have to call the right one for whatever kind of number I'm actually looking at right now, and it's a big pain in the neck. Okay? If you know that in this program you're only dealing with integers, then it's okay, or only dealing with floats. But if you're going to try to mix types, you end up doing stuff like this. Some of those languages, because their designers aren't idiots and they know that nobody wants to do this, invent sort of mechanisms on top of mechanisms to let you type both of these at once by having essentially a variable for the type that you then give, you know, first you say do this for integers and then you say do it for floats. But that's the sort of thing that we get for having types attached to data, is that we can have heterogeneous data. We can mix things up, and it doesn't matter. Okay? So that's a little piece of sort of programming language design questions. Because one of the things I'd like you to get out of this course is to be able to answer the question when your sophomores and next year's freshmen come along, and somebody asks you, why isn't there just one best programming language? Okay, this is part of the answer. Right? The best programming language for writing a program once and then running it a million times might not be the best programming language for the process of development. And in fact, there are companies out there in the world where they'll use something like Lisp in the early stages of developing a product, because they can come up with new versions and tweak up the user interface and so on and get it just right. And then finally, when everything is just the way it's supposed to be, they'll re-implement it in something like C or C++ or Java so that it runs fast. Not so much Java fast, but the other ones run pretty fast. OK, so that's the story on type tags. Let me stop and see if there are questions. Not a single question. OK, who's with me? OK, good. All right, so now we know how to deal with data types. And now the question that comes up is, there are certain operations that we want to perform on our data. And sometimes it's the same operation for different types, like the example of I plus j versus x plus y there. And so somehow or other, we have to have different versions of plus and know which one to use. And that's the problem we're going to be addressing for the rest of the week. But operators that have two operands, like plus, are fairly complicated. And I like to make things simple. So I'm going to start with a different example of data types and operations. And I'm going to make a little chart to show you what we're doing. My types are geometric shapes. So I have, think of it this way. Square and circle. Whoops. And the operations I'm going to do are perimeter and area. OK? Now, what goes in the boxes? A formula, right, for how to do that. So for a square with side S, what's the perimeter? 4s. What's the area? S squared. OK, for a circle of radius r, what's the perimeter? 2 pi r. And what's the area? Pi r squared. Great. Except I hope that you understand by now that I'm not really going to do it quite like this. I'm not going to put formulas as pieces of text. What I want to think about is functions. So I'm going to think S maps to 4s, S maps to S squared, R maps to 2 pi r, and R maps to pi r squared. OK, so that's what's in my head. So for this simple example of two data types and two operations, I have 4 procedures. OK, now think about integer, rational, real, complex, plus, minus, times, divide, integer, rational, real, complex. So there's 2 data types involved, left operand and right operand, and 4 possibilities for each of those, and 4 operations for a total of 4 times 4 times 4 is 64 functions we have to keep track of. OK? So that's already a pain in the neck, and that's, there are more types and more operations than that. So that's why I'm starting with a simple case. But I want you to understand that the subtle mechanisms we're going to invent for dealing with this problem are worth inventing because real problems are more complicated than the ones I'm showing you today. Okay? So the first thing is let's make some data with type tags attached. So I have procedures make square. Whoops, I'll do that. What I want to do is define S4 to be make square 4. And the value of that, just to get clear, is a pair whose car is the type tag and whose gooder is the value. And I'm going to say I'm going to say define C4 to be make circle 4, and define S5 to be make square 5, and define C5 to be make circle 5, just to have a little data around to play with. And now we're going to look at how to organize all this information about the methods for doing some operation on some data type. Okay? And there are 3 ways we're going to look at doing it. And the first one, the book calls conventional style. It's called that because it's kind of the obvious way to do it. That's what people did for a long time before computer scientists came around to, try to improve things. Namely, it goes back to that thing I keep talking about nouns versus verbs. And when you're thinking about how to do an action, the most obvious thing for people is to organize their thinking around the verb. Right? So here's how to build a house. And within that, there's how to build a house with a wood frame, and how to build a house of masonry, and how to build a house out of plastic prefab panels, and so on. And it's all under the heading of how to build a house. Okay? So up here, we have a procedure area that takes one of these shapes as its argument. And it says, OK, what kind of thing am I looking at? Am I looking at a square? So that's this question right here. So is the type tag of the thing I'm looking at the word square? If so, I'll just return contents of shape times contents of shape. Contents is the number that represents, in this case, the side of the square. So if I say down here, area of S4, I get 16. Area S5, I get 25, right? The side of the square of the side of the figure. Okay, if not, then is this a circle? If so, the area is pi r squared. So if I ask for area of C4, I get pi times 16, which is about 3 times 16, which would be 48. This is 50, close enough. Area C5, I should get something around 75 or 80. Yep, there we go. Okay? Any questions about how this works? Great, this is the easy one. So on my picture, this is conventional style, where we group things basically by the columns. So everything having to do with a particular verb, find the area, all the different ways of doing it for the different data types are grouped together. Okay? Well, that's not so bad, is it? It's straightforward to write. It does do the job of sort of grouping the ways of doing something together so you can find them. You don't have to dig through 64 different little procedures. So that's all fine. The only problem with this is, whoops, if I decide later on that I'd also like to be able to deal with regular hexagons or spheres or triangles or something, I'm going to have to go into code I've already written and edit it. I'm going to have to edit my area procedure, and there's the similar perimeter procedure here that has the same structure. And I'm going to have to find all of those things and put in an extra cond clause for whatever shape I want to add. Now, the trouble about going back and editing procedures you've already written is that you introduce bugs. And anytime you write code, you might introduce a bug in your new code, but here you run the risk of introducing bugs into code that used to work. For example, by getting the parentheses wrong. Okay, by putting your new clause in the wrong place. Like inside one of the existing clauses or something like that, would break code that used to work. So whenever possible, our goal is not to ever have to go back and change working code in order to add new features. So that's something to remember about designing a program. So how are we going to do that? The first way we're going to look at is data-directed programming. So that chart I have over on the chalkboard, so far, it's just something in my head, okay, that here's how I'm mentally organizing the problem I'm trying to solve about different shapes and different operations on the shapes. But we can also say, let's take this thing, this whole thing, and find a way to encode this chart as data in the computer. And this is called data-directed programming. Data-directed programming means that we're going to write one generic operation that does everything. And the way it knows what to do in particular is by looking things up in an actual two-dimensional table like this. Now, how do we build such a table? Well, we don't do that for another week. 2 weeks? 2 weeks, 3 weeks. We're going to build tables. For now, we just give you one. And the way it works is this. You can say get and no, it's good. Let's say this. Address. And it says false, meaning I don't have that in my table. Now I can say put Brian address 781 soda. And now if I say get Brian address, it will tell me whatever I put in the table. Okay? So that's get and put. It's a two-dimensional table. That is to say, the get operation takes 2 keys for a row and a column. And the put operation takes 2 keys and a value to put in that place, because that's what we happen to need for this problem that we're solving. But we'll see later on when we talk about tables, how to implement them, that you can make one-dimensional tables or 3-dimensional tables or multi-dimensional tables. But this one happens to be a 2-dimensional table. And there's only one table right now. Later on, we'll learn how to make lots of tables. But for now, there's only one of them. And it's just there to begin with. Is this functional programming? Functional programming, yes. Functional programming, no. I'm not sure. Oh, come on, wake up. You can say I'm not sure. Okay. I'm seeing a lot of I'm not sure's. I'm seeing more no's than yeses, which is good. It's not functional programming, because look at the two gets. I called the same procedure with the same arguments, and I got different answers. Okay, so the procedure get has a behavior that depends on what else has happened. Namely, it depends on the fact that I did this put. If I did a put again with a different value in there, then another get would get yet a third result. Is that a hand up? Yeah. There's a good question. Is put functional because it returns OK every time you call it? So it's sort of the constant function of its arguments. No, because even though its value is predictable just from the arguments, it changes the world in some way. So anything that changes the world, like print, for example, is considered non-functional, as well as things that depend on the changes in the world, like read. Okay? So this is not functional programming. However, we're going to make an agreement here in this room that the way we're going to use this table is right at the beginning of our program, we're going to have a bunch of puts, and then we're never going to do any puts anymore. Okay? So we're going to set up this set of how to do what, and once it's set up, we're going to leave it alone for this running of the program. I mean, later on, we might come in and invent another data type or something. But for any particular time through the program, we're only going to do puts right at the beginning, and then we're never going to change anything in this table. And once we make that agreement, we can think of the gets as being functional. Okay? Because we know that it really did depend on us having done those puts. But once we've done them, we're always going to get the same answer for the same keys, the same two arguments. Right? So here's how this works. Actually, let me start. Whoops. That's not what was supposed to happen. Let me start by actually loading this stuff all in. Okay. So the table mechanism, the put and get, doesn't care what values you put in the table. Like I put in a sentence that was my address before. But for our purposes in solving the problem of generic operations, what we're going to put in the cells is functions, right? Like S maps to 4S. And the way in Scheme we say S maps to 4S is this, right? You say lambda S times 4S. Okay, questions about that? Somebody's hand was up before. Okay, good. So I have two data types and two operations, and that's 4 different ways of doing things. And here they all are. And you should look at the 4 puts and look at the thing on the chalkboard and convince yourself that one is a representation of the other. Okay? So this should be your first glimmer of what I mean when I talk about data-directed programming. Because this table is data. Right? This is a data structure in our computer program. And in that data, there's instructions for how to do things. So now I can write what you see underneath the puts on the screen right here, which is a general procedure for doing any operation on any data type. Here's how it works. starts by saying, let's look up in the table the type tag of my operand and the name of my operator. Okay, so I have type tag will be square, and op will be perimeter. Right? So we look that up, and we get square perimeter, and what we find is lambda s times 4s. So now there's this if. What does if proc mean? What am I testing here? Yeah, is there a table entry or not? Because remember that get, if there isn't a table entry, returns false. This, by the way, speaking of programming language design, this is a little different from the way most things work. Mostly, if you ask for something that's not set up, that you can't do, you don't get back false, you get an error message, and your program stops dead in the water. Right? This table was designed so that no matter what keys you give it, it never gives you an error. Instead, if there is no such cell in the table, it just gives you false, and you can then test for that. And in this case, what we do if we get false is we give an error message. But you'll see later on that in some more complicated versions of this, if what we get back is false, we try again with different keys. Okay, so that's why it's useful to have the table return false rather than an error message. But let's say it doesn't return false, then what it returns is a procedure, and we can call that procedure on contents of obj, not just on obj, because obj is a pair, like square dot 4. We can't take square dot 4 and multiply that by 4. We have to take the 4 and multiply it by 4. So contents of obj is the actual number without the type tag. And that's the thing that we're going to use as the argument to proc. Questions about that? Okay. So you see that this operate procedure doesn't know anything about squares or circles or areas or perimeters. We could load up the table with a completely different kind of problem. We could put in arithmetic operators. We could put in stuff like magnitude or square root or something. And the operands could be integer, rational, real, complex, or whatever. And operate would work just fine. Right? So operate is a truly generic function for doing any operation on any data type as long as we've set it up in the table. So we say something like operate, and the operation I want to do is, let's say, area on C4, or operate, quote, area on S4, and the right thing happens. Okay? So we got here by doing a lot of stupid detail work about put, but I'd like you to see that we're in a truly beautiful place, that we've separated out the issue of finding the particular way to do this function of this operand from the general question of, I want to do an operation on an operand, please do it for me. So you can build a programming language that reads in a verb and a noun, like some of the earliest role-playing games, before they had graphical interfaces with mice and things. You would type in something like go right, or take wand, or attack troll, right? And those things were verb noun. And those games were written exactly like this. there would be a general procedure that just says read the verb, read the noun, and then look up in a table how to do this kind of thing on that kind of data. Okay? So it's a complete different universe from what we've been talking about, and this idea still works. Okay. We're going to see in a bit, later on, probably Friday, that we can expand this idea to deal with operators with two operands, like the arithmetic ones. Now, we haven't done that yet, but it is doable. So that's one thing we're going to do. Let's see, when are we going to do that? Oh, yeah. We're not going to do it yet. Oh, yeah. The book, by the way, this procedure that I've called operate, there's one in the book called apply generic, which is the same idea. Theirs is written for two operand operators, so it's a little more complicated. But so this operate means the same thing as apply generic. I'm not quite done here, because this notation that we're using to ask for the area of the square is a little ugly, right? It was better when I could say area S4 and get an answer. So we're going to fix that like this. By defining procedures area and perimeter. So I can say area S4. I got the right answer. Perimeter C5. Whatever. Okay? But all those procedures do is call operate. So this is what people call syntactic sugar, meaning the real work is done by operate, but to make users happy, we wrap the call to operate in a procedure that is nicer for human beings to use. Okay? But the essence of the job was writing operate. This other stuff is just frills on top of that. Okay? Now, really important, don't please get the idea that the name data-directed programming means you have a two-dimensional table that's used for keeping track of operators and operands. We are using data-directed programming for that purpose now, in today's class. But data-directed programming is a much more general idea. So back in the old days, it used to be that every company, we're talking about the days when computers were half the size of this auditorium and cost $1 million. So every company that wanted to use a computer would not only get a computer, they would hire a bunch of computer programmers. Because you couldn't just go to CompUSA or Best Buy and pick up TurboTax or whatever. That whole software selling mechanism didn't exist, and instead everybody wrote their own software. So for instance, computers were mostly used for boring things like payroll, printing out the checks to the employees every month or every week or whatever. And each company had their own payroll program. Okay, today that seems really stupid. Today you would expect to go to the store and pick up something called payroll software and stick it in your computer and it would just work. Okay? Why did each company have a separate one? Well, company A has 7-digit employee IDs. Company B has 4 digits plus a letter employee IDs. Company A pays every month. Company B pays every 2 weeks. Things like that. Little things like that meant that each company wrote their own customized to their situation payroll software. Okay? What changed that? It's still true that company A has 7-digit employee IDs and company B has 4 digits plus a letter. And it's still true that this one pays monthly and this one pays biweekly. What's different? When you use software, how do you deal with stuff like that? What'd you say? I didn't hear. Sorry? Templates, sort of, yeah. Templates is a specific case about editing and stuff. Or, oh, I see, you mean like Java templates. Yeah, no. I'm talking about the guy in payroll who wouldn't know a Java program if it bit him. But he can still set up his payroll program. Why? Give you a hint. Preferences, yeah. So what's preferences? Well, it's a data file that tells the one generic payroll program how to deal with the particular needs of this particular company, right? That's data-directed programming. And it was the reason for the first big dip in the hiring of programmers, right? Used to be every company with a computer had a programmer or two or three. And then it got to where you could be a company and use computers and not have any programmers on staff because you could use generic software courtesy of data-directed programming. Okay, so it's a big, important idea in the world. You'll see initialization files. Who runs Windows at home? Boo. On your computer, there are a bunch of files with names like such and such .ini. Stands for initialization. Those are data-directed programming files. Okay? Who runs Linux or Mac OS or any Unix thing? Okay, on your computer, there are a bunch of files called such and such .rc. Those are data-directed programming structures that tell programs how you want them configured. So this is used by pretty much every program in the world. Okay, there's an initialization file in which you can customize things. So a very, very, very important idea. I am now going to show you the most interesting use of that idea. Okay, so this is an excerpt from something in the scheme reference document that's in volume 2 of your course reader. This isn't the whole thing, it's just a little piece of it. And this is the formal syntax of scheme. This is a description of what a scheme program looks like. And it says, what does an expression look like? Well, it turns out that formally there are exactly 7 kinds of expressions. So when we looked at the little scheme interpreter, and I said there were 4 kinds of expressions, this is the same idea. So the first one is a variable, which we looked at as an expression type. Literal means self-evaluating. Procedure call is a procedure call. And the other 4 are special forms. And it turns out, according to this scheme standard, there are 3 sort of primitive special forms, lambda and cond, and one we haven't seen yet for assignment. And everything else, all the other special forms, are defined in terms of those. Okay? So what I want to look at right now is what does a lambda expression look like? It looks like an open parenthesis, followed by the word lambda, followed by formals, whatever that means, followed by body, whatever that means, followed by a closed parenthesis. So the thing in brackets, angle brackets, less than, greater than, those are sort of meta variables. They're not scheme variables, they're formal syntax variables about scheme. So we have to know what formals and body means. Formals is the formal parameters of the procedure, and it consists of open parenthesis, followed by 0 or more variables. And the 0 or more is what this asterisk means, followed by a closed parenthesis. So that's the syntax for a fixed number of arguments. Or a single variable not in parentheses which means the variable number of arguments notation with no fixed arguments, or this hybrid thing where we have open parenthesis followed by one or more variables, which is what this plus sign means, followed by a dot, followed by a variable that's the rest argument, followed by a closed parenthesis, and so on. Okay? I'm not going to go through the rest of it, but this is the formal syntax of scheme. And back when this formal notation, which is called BNF, or Backus-Naur form, when it was first invented, it was just for telling people what the syntax of a programming language was. But today, you can get a program that you're not allowed to call a compiler, even though that's what everybody calls it, because Professor Hilfinger will get upset. So for him, you have to call it a parser generator that takes something like this as input and turns out a compiler for your language, whatever it is. So I can put this into a compiler, and out comes a scheme compiler. The reason Professor Hilfinger doesn't want you to call it that is that there's a whole other aspect to compiling which has to do with what do these forms mean. So knowing what a lambda expression looks like doesn't tell you what scheme should do with the lambda expression. And that comes from a formal semantics notation, which is the other half of it. Okay, but this half generates the parser, the thing that looks at stuff that you type in and figures out what kinds of expressions are involved. So now you basically write one compiler that's sort of the universal language compiler, and then you just write a BNF for whatever language it is that you want to compile. So this is the ultimate, I think, in data-directed programming. A big, big important idea. See you Friday.